Alright, I'll just zoom this a little bit so that we can see it a little better, and we will start. So alright, we're going to start from, if you can take out your notes packet, and you will need your formula sheet also. So in the notes packet, if we can go to page 10, that's where I'm going to start from. So please go ahead and take that out and go to page 10 and have your formula sheet ready too. Before we start page 10, I know I had completed page 9 in the class. Basically it was 7.2. I had just about started the sum and difference formula. So on the formula sheet, it was the back of the formula sheet, which is right here. So this is the one that contains the sum and difference formula. And when we did page 9, we talked about, I had said, when you're looking at the formula, just look at the green sheet. And I had talked about, we filled in the first quadrant because I had said we would need it for when we were working on these problems for this particular section. And I had made you guys do one of the problems where we split up cosine of 75 degrees as cosine of 30 plus 45. So that's the premise of this whole particular section, that you're given an angle that is not on the unit circle, but you rewrite it as a sum or difference of two angles that are on the unit circle. And that instructions are right here. The instructions, that's why it says determine two values whose sum or difference is equal to the given value. That's the premise of this whole section. Okay, so just take a few minutes and just quickly go over it so that when we start page 10, you're kind of caught up with where we left off last class. That would really be helpful. Alright, so I'm going to start with the first problem. It says find the exact value of 17 pi by 12. As you can notice, in the previous problem we did cosine of 75 degrees, so we were working with degrees, and now we're working with radian, which basically means we're working with fraction. The concept is the same, except you will find two fractions that add up to 17 pi by 12. And I think that's what gets a little tricky for some of the students, because it's sort of easy to split up a number as the sum or difference of two numbers, little more trickier to do fractions. But having said that, we will go through a methodology and hopefully that will help. So find the exact value of 17 pi by 12. I know 17 pi by 12 is not on my unit circle. So basically, I will split it as two numbers that are on the unit circle. So let's do this. 17 pi by 12. And let's try see if I can add two numbers to give me 17 pi by 12, which are on the unit circle. So what I tell my students is start with, we know that when you're splitting fraction, as long as the denominator stays the same, I can split the numerator into two numbers by adding the two numbers. So for example, I can say pi plus 16 pi gives me 17 pi by 12. This is actually nothing but pi by 12 plus 16 pi by 12. Yes, everybody agrees with me? The problem with this is, so and then you simplify it, and then you simplify. Pi by 12 simplifies only as pi by 12. But 16 pi by 12, they're both factors of 2, so this also 4, so this is actually 4 pi by 3. Yes, this is on my unit circle. Yes, everybody remembers 4 pi by 3 is on your unit circle, but this is not on my unit circle. So this combination will not work. So basically, I tell my students that for you to split it, just start with the smallest number added with the next number. So for example, this is what I'll do next time. For my next combination, I'll try 2 pi by 12 plus 15 pi by 12, right? Everybody is good? Because 15 plus 2 is 17, and that gives me what I'm looking for. But let's simplify, because I know I don't have over 12 in my unit circle, but I can simplify this. This simplifies to pi over 6 plus 15 over 12, both are factors of 3, so 5 pi over 4. Is everybody good with what I just did? And this combination works. Why? Because pi by 6 as well as 5 pi by 4 are both on my unit circle. They're both on my unit circle. So I will use this combination. So I'm going to write sine of 17 pi by 12 equals sine of, I can say 2 pi by 12 plus, but I want to go straight to this. Pi by 6 plus 5 pi by 4 Alright, so now what's happening is, this is nothing but your alpha and this is nothing but your beta. So I'm using the formula for sine alpha plus beta. I always like to use my formula sheet. Write down the formula so that I don't make mistakes. This is sine alpha, cosine beta. I'm just looking at my formula sheet and writing this down. And then you substitute. So this is sine pi by 6 plus 5 pi by 4 simplifies to sine of pi by 6 multiplied by cosine of 5 pi by 4 plus cosine of pi by 6 multiplied by sine of 5 pi by 4. After this, it's just substituting the values for each of them from your unit circle. So I know sine pi by 6 is half. This is the same as sine 30 degrees. So I know cosine 5 pi by 4 is square root of 2 over 2, except 5 pi by 4 is in my which quadrant? 1 pi by 4, 3 pi by 4, 5 pi by 4. Cosine is negative here. Only tan is positive here. So it's going to be square root of 2 over 2, but negative. Cosine of pi by 6 is again cosine of 30 degrees, that is square root of 3 over 2. And sine of 5 pi by 4 is also negative square root of 2 over 2, because third quadrant both sine and cosine are negative. And then you just continue to simplify. How do you multiply fractions? Top to top, bottom to bottom. Negative square root of 2 over 4. Again negative square root of 6 over 4. And this can be written as negative square root of 2 minus square root of 6 over 4. This is an acceptable answer. Or, remember, you can always rewrite, you can write it in any form. I can pull out the negative. I don't know why I put a parentheses there, sorry. Maybe just box it. I pull the negative out, square root of 2 plus square root of 6 all over square root of 4. This is another way. Because all I did was pull the square root out. Both of them are acceptable answers. The reason I'm saying this is because if it's a multiple choice, or if you come across the answer in this form, remember they're all same answer written in different forms. Alright, so that is your problem number 2 on your notes packet. Okay, I'm just going to keep moving. Next is find the value of 13 pi by 12, tan of 13 pi by 12. So my first job is to figure out two angles whose combination is 13 pi by 12. Whose combination is 13 pi by 12. So maybe you guys can hit pause on the recording and see if you can find two angles that add up to 13 pi by 12. So use the same procedure that I talked about, where you take start the smallest, 1 pi by 12 plus 12 pi by 12, 2 pi by 12 plus 11 pi by 12, and see which combination works. So maybe try it, and then I'm going to go ahead and do the work. And remember, it can be sum or difference. So whatever combination, there can be many numbers of combination. So maybe I'll start with instead of 2 pi by 12, I'm jumping to 3 pi by 12, just like that, plus 10 pi by 12. This simplifies to 3 over 12 is pi over 4. 5 over 12 is, 10 over 12 is 5 over 6. And I noticed that both of them are on the unit circle. I knew this just looking at this because I have a little more experience, so I didn't even go into checking, so I knew this worked. Any of you who tried 2 pi over 12 plus 11 pi over 12 would have seen that it doesn't work, because 2 pi over 12 works, but 11 pi over 12 is not on my unit circle. But 4 pi over 12 plus 9 pi over 12 would have worked. So you just have to find combinations. Yes, everybody agrees? Anyone who tried 12 pi over 12, 2 pi over 12 plus 11 pi over 12 gives me 13 pi over 12. This simplifies to pi over 6, that works, but 11 pi over 12 does not simplify, and there's no 11 pi over 12 on the unit circle, so this whole combination does not work. So that's why I jumped straight to that. So this is my alpha, this is my beta. So let's go ahead and write down our formula for tan alpha plus beta. So tan alpha plus beta is, okay, let's just look at the formula sheet. Sorry, I'm running out of space here. I should have written it above. But basically, if you look at the formula sheet for tan alpha plus beta, it is tan alpha. I'm just looking at this formula sheet. So tan alpha, so tan of pi over 4 plus tan of, I'm just following this. Tan of pi over 4 plus tan of 5 pi over 6. Everybody good? Over, and then it says 1 minus tan alpha tan beta. So 1 minus tan alpha tan beta. Everybody good? I'm just going to wait to see, make sure that we all understood this. Now it's just a matter of substituting and solving it. Tan pi by 4 is 1 and tan 5 pi by 6. Where is 5 pi by? So we know that tan pi by 6 from the first quadrant, the value of tan 30 is square root of 3 over 3. Is it positive or negative? Tan 5 pi by 6 falls in my second quadrant. Pi by 6, 5 pi by 6, 7 pi by 6. Second quadrant, tan is negative. So it's negative square root of 3 over 3. Tan pi by 4 is 1. And tan 5 pi by 6, we just said it is negative. Let's go ahead and rewrite it. 1 minus square root of 3 over 3 over complex fraction. How do you simplify a complex fraction? I want to simplify. Remember, the method to simplify a complex fraction is to multiply numerator and denominator with the common denominator. There's only one common denominator, that's 3. So I multiply top and bottom with 3. So 3 times 1 is 3. And then when I multiply this with this, these two get cancelled. I'm left with, and the same thing, 3 plus these two get cancelled. So I'm left just with square root of 3. This looks like a good solution, except I have a radical in the denominator, and you always want to rationalize the denominator. And remember, I can't just multiply by square root of 3. It's part of 2 terms. So whenever you have 2 terms, you want to rationalize this by multiplying by its conjugate. What is the conjugate? A plus B, A minus B. Do you guys remember this? Whenever you're trying to rationalize a denominator which is part of a binomial, you multiply the binomial by its conjugate. Conjugate means A plus B gets multiplied by A minus B. Why? Because if I just multiply by square root of 3, square root of 3 times 3 is still 3 square root of 3. This will go, but this will become 3 square root of 3. That's why you multiply by its conjugate. Why do you do that? You do that because, okay, going back, just always going back to some of the basic stuff. I'm just going to go ahead and write here. Remember, when you multiply A minus B multiplied by A plus B, it's the same, reverse of the factoring is A square. That's why it's important to know these patterns. A square. Factor of this is this. Multiplying these two gives you this. That means when you multiply these two, it's A square minus B square. Because both are square, there will be no radical that's left at all. Let's take care of the denominator. A square, 3 square is 9 minus B square minus square root of 3 square is 3. Did everybody get that? 3 square minus square root of 3 square. That's what we basically wrote. A square minus B square. But the numerator is a little more work. You have to FOIL it. So 3 times 3 is 9. 3 times this negative square root of 3 is negative 3 square root of 3. Okay, yeah, everybody good? And then you multiply negative square root of 3 with this. So it's negative 3 square root of 3. And then negative square root of 3 times negative square root of 3 is positive 3. Okay, let's continue simplifying this. So yes, so this does require some work because it is rationalizing the denominator, which is a binomial. If you stop your answer here, sure, I'll give you points because you did all of this. I'll probably take off 25% of your points for not rationalizing the denominator. So that's why it's important for us to, we did this in the rational, when we did the semester 1 rational functions, this is one of the things we did. Okay, so this is nothing going to be but, so combine the like terms, 9 plus 3 is 6. You add these are like terms because they both have the same radicand. So negative 3 becomes negative 6 square root of 3. And my denominator is 6. Again, a good answer, except it can be simplified because both of them are factors of 6. So you can pull 6 out. What am I left with? 1 minus square root of 3. And 6 stays as 6. So this simplifies to 1 minus. That's your final solution. Okay, I'm going to stop here. And we'll continue the remaining of the same page on part 2 of this page.